Assalamualaikum warahmatullahi wabarakatuh. In this video, we will talk about mass and energy balance for single effect evaporator. Assume that we have a diluted orange juice. Solid is the original orange juice and solvent is water. And we want to concentrate that solution using a single effect evaporator. So we introduce the feed, which is the diluted orange juice, at a mass flow rate F kg per hour with the temperature Tf, enthalpy Hf, and the total mass fraction of solute in the solution Xf. The feed is heated by saturated steam that enters the evaporator at a mass flow rate S kg per hour with a temperature Ts, enthalpy Hs. The steam doesn't mix with the feed. The heat transfer happens through the pipe, so the steam is only condensed and left with an enthalpy Hs. The temperature is the same during the whole process since the steam is saturated. The steam only gives off its latent heat, noted, lambda equals to capital Hs minus small hs. The diluted orange juice inside the evaporator boils at a temperature T1, which is the temperature of the solution at boiling point. The boiling point of the solution is proportional to the pressure inside the evaporator. The higher the pressure, the higher the boiling point will be. While boiling the solution, the vapor is produced and the solution is concentrated. The vapor leaves the evaporator at a mass flow rate V kg per hour, enthalpy Hv, and the total mass fraction of solute in the vapor, Yv. We assume that it has the same temperature T1 when leaving the evaporator. The concentrated juice obtained leaves with a mass flow rate L kg per hour, enthalpy Hl, solute content Xl, and temperature Tl. Since the solution is being concentrated, Xl is higher than Xf.
We'll first look at our mass balance. The mass balance of the system in terms of time is mass in minus mass out plus mass generated minus mass consumed equal to change in mass of the system over time. There is no mass generated or mass consumed as no reaction occurs in the evaporator. So here on out, the equation becomes mass in minus mass out equal to change in mass over time. Mass going in include feed F, which is dilute orange juice, and saturated steam S, while mass going out include vapor V, product L, which is concentrated juice, and condensed steam S. Substitute that into our equation and we get F plus S minus V minus L minus S equal to change in mass of the system over time. The amount of steam entering and leaving the evaporator is the same, so our balance is further simplified into F minus V minus L equal to change in mass of the system over time. If we assume that there is no significant changes of values of the properties at all the points of the evaporator, the system will be considered at steady state, where change in mass of the system over time will be 0. Thus, the equation becomes F minus V minus L equal to 0, then F equal to V plus L. Next, we'll discuss the mass balance of the solute of the system, which is the actual pure orange juice. We'll again take mass in equal to mass out, where mass in is our dilute F and mass out consists of vapor V and concentrate L. Substitute it, we get feed flow rate F times by feed concentration XF equals to vapor flow rate V times by vapor concentration YV plus product flow rate L times by product concentration XL. So FXF equal to VYV plus LXL. If the vapor is a pure solvent, then YV is equal to 0, so FXF equal to LXL. Finished with the mass balance, let's move on to the energy balance of the system. It follows the same pattern as the mass balance: energy in minus energy out plus energy generated minus energy consumed equal to energy accumulated in the system over time. As mentioned earlier, no reactions happen during evaporation, so energy generated and energy consumed is equal to 0. We'll get energy in minus energy out equal to energy accumulated in the system over time. Energy here consists of work W, heat Q, and mass flow rate times enthalpy, kinetic energy, and potential energy. For work, evaporators are passive devices, so we assume there is no work done. For heat, we assume the evaporator is well insulated, and there is negligible heat transfer out of the system into the surroundings, so Q is equal to 0. We're left with M in times delta H in plus PE in plus KE in minus M out times delta H out plus PE out plus KE out equal to energy accumulated in the system over time. We can assume that the kinetic energy of the system is equal to 0 even though the fluid is flowing, because in most cases the flow of the fluid will be relatively slow so that the heat transfer between the fluid and the steam can take place. The potential energy in the system can be assumed equal to 0 since there is not much difference in height. However, it should be considered when dealing with tall evaporators. The energy balance of the system will be governed mainly, in most cases, by the enthalpy. So, M in delta H in minus M out delta H out equal to energy accumulated in the system over time. Our inputs are feed and steam, and our outputs are product, vapor, and condensate. Substituting in FHF plus S capital HS minus S small hs minus VHV minus LHL equal to dE CV over dt. Steam input flow rate is same as steam output flow rate, so FHF plus S times by capital HS minus small hs minus VHV minus LHL is equal to dE CV over dt. At steady state, change in system energy over time is equal to 0. So FHF plus S times capital HS minus small hs equal to VHV minus LHL. As capital HS minus small hs is equal to latent heat lambda, we get FHF plus S lambda equal to VHV minus LHL, and that is our energy balance.